Moving now to section 4, point and interval estimates of the population mean. Statistical inference consists of two branches, hypothesis testing, which we'll cover in the next reading, and estimation, which we will talk about here. To make this segment more interesting, I will ask a simple question. What was last month's average return on all publicly traded stocks in Asia? This question is difficult to answer because there are so many stocks across so many different exchanges in several countries in Asia. So to come up with an answer, you probably need to do the following. You need to draw a sample from the larger population, and as we've discussed earlier, probably you might have to define various subpopulations and do some stratified sampling. But in any case, let's say you come up with a sample and then you estimate the mean of the sample in order to estimate the mean of the population. You then also might want to come up with a range of possible values of mu based on X bar and your sample size and so on. And that is what we are going to talk about. Now, let us say that the X bar number that you come up with is 10%. So 10% then becomes your best estimate of the population mean. And the 10% is called a point estimate because that is the 1 point estimate of the population mean. The estimator is the formula or the process that you use to come up with the point estimate. So how did you come up with the 10%? Let's say that your sample size was 30. What you essentially did was take the average of the 30 stocks that you identified. So if your sample was 30 stocks, you simply did the return on the first stock plus the return on the second stock all the way to the 30th stock divided by 30. So this formula or the process is called the estimator. From an exam perspective, you need to understand the desirable properties of an estimator. The first one is that the estimator should be unbiased, which means that the expected value of the estimator is equal to the parameter. The idea here is straightforward. You have this population with a mean equal to mu. When you draw a sample, the expected value of the sample mean should be equal to the population mean. If this is the case, then we say that the estimator is unbiased. Next, the estimator should be efficient, which means that the variance of the sampling distribution must be smaller than all other unbiased estimators. So essentially, the variance or the standard deviation of x squared must be smaller than the variance of any other estimator, and that is what makes this efficient. And finally, the estimator must be consistent, which means that the probability that the estimate is close to the value of the population parameter increases as the sample size increases. So initially, if you took n is equal to 30 and then you increase the sample size to 50, the probability that x bar is closer to mu should increase with a larger sample size. If that is happening, then we say that the estimator is consistent. Here is the sort of question that you might get. And the answer is fairly straightforward given what you have just heard. The answer is A, but you have to remember this material because on the exam it might be harder to recall these definitions. Next, we talk about the confidence intervals for the population mean. So you have an estimate for last month's average return. So that was your point estimate of 10%. You are then asked the next logical question, which is how sure are you about this 10% number. Now clearly you can't say you are 100% sure, because if the manager then goes and checks all stocks, or let's say the manager goes and picks 200 stocks and the return is different from 10%, then obviously you'd be wrong. So perhaps what you need to do is give a range. That range would be around 10%. But to make things a little more concrete, you are told that you need to identify the range with 95% confidence. And what this means is, if you give a range from say 8 to 12 and you say you are 95% confident of this range, then if the manager goes and identifies 100 stocks at random, and if it turns out that of those 100 stocks only 80 fall within this range, then clearly you will be wrong. On the other hand, if the manager goes and picks 100 stocks and 97% fall within this range, then you are okay with this statement. So what we are now going to talk about is, how do we come up with a range of possible values for the population mean given a certain level of confidence. Here is the basic formula we'll use. The confidence interval, which is essentially the range, is your point estimate, 10% in our case, plus or minus a reliability factor times the standard error. We've already talked about the point estimate. Now we are going to understand reliability factor and standard error. Standard error, as we've discussed before, is given by sigma over root n. Sigma is the standard deviation of the population. N is your sample size. So in our example, let's say sigma is equal to 3, and let's say that we pick a sample of size 100, then sigma over root n is going to be 3 over root of 100, which is 0.3. The reliability factor is sometimes called Z alpha over 2. And the way you can think of this is as follows. Let's say that we want to come up with a range with a 95% confidence level. So 95% means 0.95. That is our confidence level. If we look at a standard normal distribution or a Z distribution, and we have 0.95 probability in this range, then essentially what we have in the two tails is a probability of 0.05, which is 1 minus 0.95, and then in one tail over here we have 0.05 divided by 2. The 0.05, which is essentially 1 minus 0.95, is sometimes called the alpha or the significance level. And in one tail, we are going to have half of alpha. That's why we use the symbol alpha over 2. If you look at your Z tables and you have a situation where 0.95 is in the middle, this is 0.025, and then obviously this is also 0.025, then you will notice that the Z value, which corresponds to a cumulative frequency of 0.95 plus 0.025, this Z value is going to be 1.96. So for a 95% confidence level, the corresponding Z value given a normal distribution is 1.96. If your manager says that he wants 99% confidence, then clearly we will need a higher reliability factor. But let us just come up with a range given 95% confidence and given this value for the standard error. Essentially, our answer becomes 10%, which is our point estimate, plus or minus the reliability factor, which is 1.96 times 0.3. So this essentially is our range. If we come up with the precise numbers, we'll get 9.412 to to 10.588. So essentially we are saying that we are 95% confident that the population mean falls between these two numbers. Now, as I was saying earlier, what if you are asked to give a range with 99% confidence? Notice that the point estimate will stay the same. The standard error, which is sigma over root n, will stay the same. But if you are operating with 99% confidence, then the z value is going to increase. So z alpha over 2 will go up, which means that you will then have to give a wider range. And this makes sense because if you need to speak with 99% conviction, then obviously you will have to give a wider range. If you think about what your manager might do to test whether your statement is accurate or not, he might go just sample 100 stocks. And if you are speaking with 99% confidence and he finds 97 stocks which have a return within the range and 3% that are outside the range, then obviously you will be wrong. So to cover yourself, you need to give a wider range when the confidence level is 99%. Sometimes you will notice this confidence interval or range expressed like this: x bar, which is simply your point estimate, plus or minus z alpha over 2, which is the reliability factor, times sigma over root n, which is the standard error. Some standard reliability factors for different confidence levels or confidence intervals. We have already talked about this. If your confidence interval is 0.95 or 95%, then we are looking at a z value with a probability of 0.025, and this z value is 1.96. If your confidence level is 90 or 0.9, then obviously the z value will be smaller, and that is 1.65. And if your confidence interval is 99%, then the z value will be larger, 2.58 to be specific. Notice that if your confidence level is 95% or 0.95, this is written as 1 minus alpha, which means that alpha, our significance level, is equal to 1 minus 0.95, which is equal to 0.05. And because 0.05 is the probability in both the tails, and we are only concerned about the probability in one tail when we come up with the z value, that's why this is written as z alpha over 2, which here is 0.05, and in the case that we've been studying, it is 0.025. This slide simply summarizes what we've been talking about, so you should read this. The only point that I will highlight is related to the reliability factor, which says that the number depends on the assumed distribution of the point interval and the degree of confidence for the confidence interval. So this we've talked about. A 95% confidence interval resulted in a z value of 1.96. A 99% confidence interval would require a higher z value, and so on. But the reliability factor also depends on the assumed distribution. So far what we have assumed is a normal distribution, so we look at the z table. Later on we will also look at something called the t distribution. Let's solve this problem now. You take a random sample of stocks on the National Stock Exchange. The sample size is 100, average Sharpe ratio is 0.5. Assume that the Sharpe ratios of all stocks on the National Stock Exchange follow a normal distribution with a standard deviation of 0.3. So we have a normal distribution. The standard deviation of the population is known. What is the 90% confidence interval of the mean Sharpe ratio of all stocks on the National Stock Exchange? So we use our formula, confidence interval is equal to the point estimate plus or minus Z alpha over 2, which is our reliability factor, times the standard error, which is sigma over root n. Our point estimate is given right here. The average Sharpe ratio for our sample is 0.5 plus or minus Z alpha over 2. We have a 90% confidence, so we look at our normal distribution. 90% confidence means we have 0.9 over here. Our alpha is equal to 0.1, which means that we have 0.1 probability in the two tails. In one tail over here, we'll have alpha over 2, which is 0.05. So if this probability is 0.05, then the Z value over here is going to be 1.65. So 90% confidence, Z value or the reliability factor 1.65. So we plug 1.65 over here, and then we have to calculate the standard error, which is sigma 0.3 divided by root n, which is the square root of 100, our sample size, so divided by 10. You solve this and you should get 0.5 plus or minus 0.05. So we can say with 90% confidence that the Sharpe ratio for the population will fall between 0.45 and 0.55. So far, we have assumed that we have a normal distribution with a known variance. And when we can make this assumption, then the appropriate statistic is the Z-stat, whether you have a small sample size or a large sample size of 30 or more. What if you have a normal distribution but the variance is not known? And this is quite a common situation. Then you cannot use the Z statistic, especially if you have a small sample size. You have to use something called the T statistic, which we will talk about over the next few minutes. If you have a large sample size and this situation, normal distribution, unknown variance, the theoretically appropriate statistic to use is the T statistic, but you can also use the Z statistic. For a non-normal distribution with known variance, you cannot make a statistical inference if you have a small sample size. You have to use a large sample size, and given that the variance is known, you should use the Z statistic. For a non-normal distribution with unknown variance, again, you cannot make a statistical inference if you have a small sample size. You need to have a large sample size, and there again, the theoretically appropriate statistic is T, but the Z statistic will also work. Let us now look at the student's T distribution, or what is generally called the T distribution for short. This distribution in blue is the standard normal distribution or the Z distribution, which is what we have talked about. You use this when you know the variance of the underlying population. But as we just said, if the variance is not known, then you should use the T distribution, and the light purple and dark purple show examples of the T distribution. Notice that the T distribution is less peaked and fatter than the normal distribution. So the T is basically short and fat relative to the Z distribution. Also notice that the T distribution depends on the sample size. When the sample size is small, then the T distribution is very short and fat. As the sample size increases, the T distribution approaches or gets closer to the Z distribution. So we say that the T distribution is defined by the degrees of freedom, and in our case, the degrees of freedom, or DF, is simply given by the sample size minus 1. You need to remember this fact. As I've already mentioned, as the sample size gets larger, the t distribution more closely approaches a standard normal distribution. Just as a side remark, I got this picture from the Columbia University website, and I would encourage you to visit this website. It has lots of useful information related to the quantitative or mathematical knowledge a student must have who is entering the MBA program, and that knowledge is fairly similar to what is required of someone who is entering the CFA program. Confidence interval using the t distribution. So let's look at an example which is similar to what we saw earlier. You take a random sample of stocks on the National Stock Exchange. The sample size is 20, so now we have a smaller sample size. The average Sharpe ratio is 0.5. The sample standard deviation is 0.3. You do not know the population variance, but assume that it follows a normal distribution. What is the 90% confidence interval for the mean Sharpe ratio of all stocks on the National Stock Exchange? So, if you recall the table that we just saw, here is a small excerpt. Notice that we have a normal distribution, but the variance of the population is not known. So the appropriate statistic is the t statistic, and this is for a small sample size, which is what we are working with. The formula for the interval, the confidence interval, is the same. It is x bar, which is a point estimate, that is 0.5 plus or minus. Now instead of the z statistic, we are going to use t. So t alpha over 2, and to look up t alpha over 2, we need the t tables. The concept of alpha is the same. For 90% confidence, alpha is equal to 0.1. So alpha over 2 is equal to 0.05. So we really have plus or minus t 0.05 times s. This is the standard deviation of the sample, which is given right here, 0.3, divided by the square root of n, which now is 20. So divided by root of 20. So the only piece of information that we now need to find is the t value for 0.05. And here is how we do this. We need to know the degrees of freedom, because as we saw earlier, the t value depends on the sample size, which in turn drives the degrees of freedom. If the sample size is 20, the degrees of freedom is 20 minus 1, which is equal to 19. We also need the confidence interval, which is 90%. 90% confidence interval is 0.9, and as we just said, alpha then becomes 1 minus this, which is 0.1, and alpha over 2 is 0.05. So we have a t distribution. What we are really looking for is this t value over here, such that we have 0.05 in one tail. If you look at the back of the curriculum where you are given the t distribution, you will be shown this information: level of significance for one-tailed probabilities. So if the one-tailed probability is 0.05, you read that off the top row, and then you also need the degrees of freedom, which equal 19 for our case. So degrees of freedom 19, probability 0.05. So you have 1.729. So this number is 1.729. Now you plug this back over here. So t is 1.729, and you can do the maths. Your confidence interval is 0.5 plus or minus 1.729 multiplied by 0.3 over 20. So let us solve this. You will get 0.5 plus or minus 1, 2. So what this means is that we have 90% confidence that the population Sharpe ratio falls between 0.38 and 0.62. Notice an interesting point here. Given that we are using a t distribution which is shorter and fatter, so with this particular distribution we don't know the population variance, so we are relying on the sample. So the reliability factor given a 90% confidence has to be larger than the reliability factor of 1.65 which we used earlier with the z distribution. So that is why over here with a larger reliability factor we need to give a wider range compared to what we saw earlier. Selection of the sample size. Now when you are pulling a sample, obviously one of the things you worry about is how big must your sample size be. If we look at this basic equation, confidence interval is point estimate plus reliability factor into standard error, you recognize that the standard error depends on the sample standard deviation divided by the square root of n. So if you want a tighter or a smaller or a more precise confidence interval, then you need a smaller standard error. You can get a smaller standard error by using a larger sample size. So all else equal, it might seem that we should simply use a sample size that is as large as possible. But we should consider the following issues when we decide on the sample size. The first is the need for precision. When we are giving a confidence interval, how precise do we need to be? All else equal, if we need more precision, we should use a higher n. A second point is that if we use a very high sample size, then we might risk sampling from more than one population. We should be sampling from the population that is of interest to us or the population that we are studying. But if n becomes too large, then possibly we might spill over to a population that we are not that interested in. So that is an issue we need to consider. And a third very important item is cost. It is expensive to draw large samples. So we need to balance precision with the cost of taking large samples. And now we come to the final segment in this reading, which has to do with the challenges associated with sampling financial data. I'll simply summarize the main points. One of the challenges is data mining bias, and this data mining bias comes from finding models by repeatedly searching through databases for patterns. The warning signs include too much digging without any real confidence and the lack of economic justification. Just to explain this, say you have a database that consists of several stocks and you want to identify the factors which have an impact on stock returns. If you simply keep digging through this database and you come up with certain factors which have a statistically significant relationship with stock returns, there is a chance that you will identify some factors purely by accident, or there is purely a statistical significance but no economic significance. For example, you might see that for companies where the CEO likes to wear a pink necktie, the returns tend to be above average. Now, that piece of statistical information would only be for this particular database, and it would not really help you in the future. The point being that if you spend a lot of time digging through data in a given database, you will find some relationships that are only specific to that particular database. When that happens, we say that we have a data mining bias, and you can identify a potential data mining bias in a study if you notice that the researcher is spending too much time looking for patterns in the same database and if there is no real economic justification for the statistically significant relationships that are being presented. Next, sample selection bias. This occurs when some data is systematically excluded from analysis, usually because of lack of availability. A classic example is survivorship bias, where companies are excluded from analysis because they have gone out of business. What happens here is, let's say that you are evaluating the returns on the mutual funds in a given country, and you only evaluate the mutual funds that are currently active. What you have done here is systematically excluded the mutual funds that have gone out of business over the last 5 years, and hence your estimated returns will be overstated because you are only considering the survivors, and by definition the survivors will have done better than the mutual funds that did not survive. Look-ahead bias may exist if test used data not available on test date, and a classic example is tests based on price to book value ratios, because when you use this ratio, the price is a current price at the time of the test, but the book value is likely to be the book value from a different point in time, because book values are not published continuously. When this sort of a situation occurs, you might have a look-ahead bias. I recognize that this is a very high-level explanation. You will see this in more detail at later levels. For now, you just need to memorize what you see over here. Time period bias exists if results are time period specific. Short time period may reflect phenomena specific to that period. So if you are, let's say, doing a study related to stock returns, and your study is over a short time period where the stock returns were very good, then we have a potential time period bias, because your results based on that short time period do not really reflect the overall performance of stocks. Another situation where you can have a time period bias is if the time period that you use is too long and there have been certain fundamental economic changes during that time period. So if you take the situation in India, in the 90s, the markets were opened up, and if you are now doing a study that spans from say 1980 to 2010, this is a very long time period where we've had at least one regime change or some fundamental economic changes, and studies that you do which span this long time period might also be susceptible to time period bias. We are done with all the sections in this reading. Now let's just quickly summarize the most important points. The core concept is sampling, where you have a population with a certain mean and you want to draw samples from that population and use the sample mean to make an inference about the population mean. We studied the central limit theorem, which talks about the distribution of X bar, and we learned that for a large sample size, the distribution of X bar will be roughly normal with a mean equal to mu, which is the mean of the population, and the standard deviation of X bar is going to be sigma over root n, where sigma is the standard deviation of the population and n is the sample size. If the population standard deviation is not known, then we can use the sample standard deviation. The confidence interval for our prediction of the population mean is given by X bar, which is our point estimate from here, plus or minus the reliability factor Z alpha over 2. This is based on our confidence, say 95%, times the standard error, which is sigma over root n, that is this number. We talked about the use of Z statistic versus T statistic. You use the Z statistic when the variance is known and the T statistic when the variance is not known. And finally, we talked about the biases such as time period bias, data mining bias, survivorship bias, and look-ahead bias. As always, I want you to review the learning objectives in the curriculum. Try to do the examples and practice problems, but here again, the curriculum practice problems and examples are fairly complicated. So if you don't fully understand them, that is not a huge problem. Just try to read them once or twice. It is more important that you practice problems and questions from other sources like Schwezer and so on. That will give you the necessary skills to do well on your exam.